Hello students. Today we are going to discuss about aldehydes and ketones. So this is our topic. So this is the first video in our series in which today we are going to discuss about the structure aspects of aldehydes and ketones. So how the structure is, how to identify whether it is aldehyde or a ketone, what is the feature of it, how it bondings are there. So those kind of things which we are going to look on. Now, first thing before going into the structural aspect, there are certain fancy words which we one should know. So first thing is, I will give you one small reaction. So let's say we have CH4 and then adding another molecule, chlorine, and then in presence of sunlight, say H nu, I'm showing like that. So the product is this CH3Cl plus HCl. Now, in this simple reaction, we should be able to name some fancy words. First thing you know that on the left side, whatever the molecules or atoms or ions are, we call them reactants. And on the left side, we are getting products. So I can say CH4 and Cl2 are reactants. They are reacting with each other. And by this reaction, we are producing CH3Cl and HCl. And now each of them has a different name. Let's focus what we are trying to achieve here. We are trying to change this guy. This is the main molecule, right? So the main molecule is this. We are actually doing reaction for this. We can say like that. So main molecule in which change is brought. So CH4 is changed into CH3Cl. It is the main thing. It is the main guy. And we have a name for it. We will call it substrate. So substrate is CH4. It is the main molecule in which the change is getting. So this is what what we are trying to change it to CH3Cl. So what about this guy? Okay, so this guy is substrate. Yeah, substrate. Now the second guy who's there to bring the change is called reagent. So this guy will be called reagent. Reagent. Okay, so reagent is what can be a molecule, atom, or an ion that brings the change. That brings change in the main molecule. So these fancy words we should be very comfortable with so that when we discussed while we are discussing aldehyde ketones, we should be able to, you know, tell the difference between regions and substrate. On the right side, if you see, this is what we want. So this is the main thing which we got, or we can say this is the main product. And this is the byproduct we can say, or you can say side product. So in a way you can say we are doing reaction to get this. This is just a side product. We may or may not use it, right? It is worthy for us to get it or not. We are not bothered about it. We are bothered about this guy. We are bothered about this guy, substrate. So now let us read this together. So what I want to say that I chose a substrate of CH4. I reacted it with reagent Cl2 in sunlight, in the presence of sunlight, and I got the main product of CH3Cl, and the side product was HCl. So these fancy words, substrate, reagent, main product, side product, we should be very, very comfortable with. Now let us talk about aldehyde, which you are waiting for, right? What is a aldehyde? How to identify it? Like if you go in a market and you see that, and you should be able to tell, oh, that is aldehyde. Now, what are the features? How you'll be able to see it, right? I will show you the structure here. So the most interesting thing with the aldehyde is carbon is there, yes, and then there is a double bond with oxygen. So this is the main feature which I see. Okay, I don't know what you see, but that is what we get a hint of. Yeah, maybe it is aldehyde, right? We are just seeing a cap, right? So this cap is there, aldehyde, and because the carbon is tetravalent, so it can make four bonds. So one it can make with R. What is R? We will discuss that. And one of the bond will be with H hydrogen. And this, if you find it anywhere, please report to me and tell, sir, we have found the aldehyde. So this is the structure we are going to discuss. Now, there is one thing like what is R? So R is actually alkyl group. Alkyl group? What does that mean? Alkyl group. We know only alkanes, right? You must be knowing alkanes, methanes, ethane, propane, butane. Let me discuss that first. Okay, so what is the alkane? So leave the alkyl. Alkane. Okay, so alkane will be like, I will give you an example. CH4. We call it methane. So are you hearing this? Ane, that is the alkane group. It is one of the element of alkane group. Now C2H6, this is your ethane. Yeah, C3H8, that is your propane. Prop means three, right? So meth is one carbon, eth is two carbon, prop is three carbon, and C4H10 is butane, four carbons. Yeah. So this is the generic alkane, what you can say, nomenclature. And now we can derive a formula also for this. So, just observe what is happening. If carbon is 2, H is getting 6. If carbon is 3, H is going 8. So we can say the generic formula for alkane group is CN. If C is N, and you can put any number, and hydrogen will be double of it, 2N, and then you will add 2. Okay, so this is the generic formula for alkane group. Yeah, and now see, can we apply it here? Put the value of N as 2, so you will get C2 H 2 into 2 because N is 2 now, right? For this ethane. So 2 into 2 is 4 and then add 2. Oh, 4 plus 2 is 6. So that's why we are getting ethene. If I put N is equal to 3, C3 at 6 plus 2 and that will be 8. And likewise butane. So this is what the alkene group is. Now, how can we make alkyl group? We just have to remove one hydrogen. See this? So like we had CH4, right? And if we somehow remove one H, so what will be remaining? CH3. So this is what element we got of alkyl group. And what will be the name of this? Or what was the name of this? This was methane, right? This was methane. So it will be called methyl group, right? Methyl group. So this is what we mean by this R. So in this case, this can be attached, CH3. Right? So that will be methyl group is attached, we can say, with this carbon. To summarize this, we can tell that if you do alkane and you remove one hydrogen, so remove one hydrogen from an alkane group, what you will get? You will get alkyl group. And because one hydrogen is gone, right? One bond is less. It can be bonded with something. And that's why it is getting binding here. It is CH3, let's say. So one bond, the fourth bond is getting attached with this carbon. And now discuss about this. And that is the most interesting thing, don't you think? This double bond oxygen. So what we call them, let's discuss that. So now this group, this group, which we are seeing as a hat, right? This, right? This will be called carbonyl group. Carbonyl group. This is the main thing. Carbonyl group. So first identify carbonyl group. Okay. In carbonyl group, what is there? One is carbon atom, one is oxygen atom, right? And they are different from others, right? This CH3, if here it is CH3, that carbon is different. This guy is different. This is doing different thing. It is getting double bonded with oxygen. So remember that. Okay. So to name them, because they are doing separate things, this carbon, this carbon will be called carbonyl. Let me carbonyl, carbonyl, carbon. So we are naming them very carefully so that we are not confused when we are doing reactions, when we are understanding the structure. We exactly know what everything is called. And this double bond oxygen we'll call, you can guess it, carbonyl oxygen. Now we are able to identify everything about the structure of aldehyde group. How to identify it, what are the different things. So in words, I can say for aldehyde group, okay, so for aldehyde, okay, what is the condition? At least one hydrogen, one hydrogen should be with carbonyl carbon. So remember, I have said this word at least. At least means one is fine, but it can be two also. Instead of R, we can have H here also. That will be also aldehyde. So we have to focus on, now we know what we want to see. We want to see the carbonyl carbon, which is, with the carbonyl group, C double bond O, that carbon, and that carbon should have at least one hydrogen. That is what we are focusing on to get the structure right, identify structure very, very clearly for aldehydes. Now we talk about the other structural aspect of this formula or of this compound, aldehyde, and we will focus on the bondings. So this is the structure, at least one hydrogen. Yeah. So this carbon, carbonyl carbon, in this structure, double bonded, will be sp2 carbon. So the hybrid, it will be hybridization, right? sp2, we can say hybridization will be there. Remember that even if it is a single bond, okay, well, there is a fancy name for that. So if carbon is having single bond with oxygen, so this single bond, we call it sigma bond. Remember that. And these bond, the single bond is strong. It is strong bond. This only gives the shape. It is responsible. The single bonds are responsible for the shape. Remember that. Okay. And they are formed due to the hybrid orbitals. Hybrid orbitals. Yeah. Now think about it like I'm talking about bonds. So carbon can make four bonds and it can make any number of bonds like one, two, three. Right. So if all single bonds are there like this, so we can say there are four sigma bonds. So the hybridization will be of type sp3. Remember that. One lesser than that, right? 4 sigma, one less sp3 hybridization. If it is a 3 single bond, right? 3 sigma bond it is having, then it will be our 3 sigma bond. One less The hybridization of carbonyl carbon will be sp2, one lesser than that. And what if it is 2 sigma bond? Only 2. Okay, so 2 sigma bond, one less, go one less. What will happen? sp hybridization will be there. So what about the rest of them, right? If it is 3, what will happen? See, for example, if there is one bond with carbonyl carbon, we call it sigma. If there are two bonds, remember that one will be sigma, another will be pi. We will discuss what is the pi bond looks like. And if there are triple bond, if carbon is making triple bond, one single bond will be there, stronger, and other two will be pi bonds. So pi pi. So remember that. In all the cases, if you see, all the bonds are one having one sigma bond and others are pi if there are. So we discussed like sigma bond is strong. You guessed it, pi bond will be weak, right? And how it is formed, let's see that. Now let's discuss this. If you think about this carbon and then single bond oxygen. So I have only shown the sigma bond here. I'm going to show you now the pi bond and how it is formed. So if you see the pi orbital, lobes kind of that, right? So these are the lobes and lobes of oxygen. So the pi bond is formed by the lateral overlap of these pi p orbitals. So if I want to show like how it'll be somewhat like this. They will combine and they will create like this hybrid orbital, right? By lateral overlapping with each other. Carbon's p orbital and oxygen's p orbital. And this bond is pi orbital, pi bond. This is pi bond. This is the pi bond. It's a weak one, okay? And this guy is strong one, right? That is sigma, right? Pi is a weak bond, and there are chances that it will go around, or there is a fancy word for that. Pi, remember, is a weak bond. It can be broken, and there are chances are that it will be moving around or it will be delocalized. Fancy word, a very heavy word, delocalized. Not remain a local. It will delocal. It will delocalized. Like that you can think of. And now let's see that in action. By the way, this is just a what you say representation. How we will see it simply will be like this, right? So we cannot say which one is pi bond and which one is sigma bond. We are just understanding this here, like the pi bond will be formed like this by lateral overlapping of p orbitals of carbon and oxygen. And we can, we don't have to think like upper one is the pi bond or lower one is the pi bond. We just understand this like one of them is a sigma bond and one of them is a pi bond. So seeing this, we cannot identify it, right? But we know that one of them is a pi bond, which is weaker, and one of them is a sigma bond, which is a stronger one. Now, let me tell you, what about this? What about delocalization? Oh, it can change its form. It can make, its own different images. And that is, we call a fancy word. It can, it can have resonance. Can have resonance due to because this pi bond can go around. It can be delocal. It can be delocalized. For example, let's take an example and understand. So let's say we have a molecule like this, CH2, yeah, and double bond CH, and then single bond CH, and then double bond CH2. So getting it, here it is 1 pi 1 sigma, here it is 1 pi 1 sigma, here it is only 1 sigma bond, right? So what can happen is this pi bond can be delocalized, okay? So it can come on this bond can be come on this, or electron can come on this and it will be negative. This can go to this bond, right? It can make this double bond and delocalize itself here. So what will be remaining here? Positive charge. So remember, so this double bond has gone here and this bond can travel here. So now this is what the pi bond does, right? It can be delocalized, it can roam around. So now what will happen? We can say, see, this has lost an electron, so it will become this side, we will become positive. This has remained only one single bond, sigma bond here, and pi has gone here, right? Pi bond has come here, and it has made double bond with this now. So see, the pi bond has moved or delocalized, right? And this also had broken and made CH molecule negative. And this phenomena which we are discussing, that is what is called resonance. Okay, resonance. And there is also one fancy word which we should know, which is conjugation. Okay, conjugation. Conjugation, what does that mean? When we see alternate one after the another pi bonds. Okay, one after the another, we call that conjugation. Let's go through it. So let me show you the structure of benzene so we understand that properly. So let me show, if you want to create benzene, we create this hexagonal shape like that, right? Right. And we show double bonds also. So first thing, I want to name these sides so that you are clear about it, what I'm doing. So there are 6 corners like that, right? 6 carbons actually. And now I can show double bonds like that. So this bond is a pi bond, okay? And it will be alternated. One, we will leave this gap and this, leave this gap and this. So this is called, the bonds are in conjugation, okay? Alternate pi bonds. And what is, I draw like that, same benzene structure, but what I am showing is like this. I will make a difference. All 6 carbons, I will name them like that, 6 carbons, but I will not use pi bond here. Instead, I will use them between 2 and 3 this time, and then alternate conjugation. So one left, alternate pi bonds, leave one, alternate pi bond. And these kind of structures are called resonating structures. Yeah, resonating. They are resonating with each other. Right? They look similar, but there is a difference, right? If you see them like that. Now, how to show that? And what we want to show, that what is happening in resonance, that these pi bonds are moving around. And if you want to see the hybrid of it, if you want to understand like what actually it is, or want to represent it, you will show like this. It is a benzene, and pi bonds are moving, they are alternating, and they can be in any side. So for that, we will show like this, a circle kind of, a dotted line, some people say in some textbook. So that is what is called, not a structure this time, they will call them resonance hybrid. And this is the better way to show the benzene. Now, what happens if we are having like this, if we are having structure like that, or resonance hybrid, pi bonds are moving around, they are getting delocalized. What is the point of moving around? Because they are moving around, they behave like they are helping everyone. So the bond length, every bond length is same. Or we can say they increase the strength everywhere, right? So the strength, bond strength is also same. And by delocalization, what they are going to increase is the stability. So they are increasing the stability of this molecule, right? So think about it like these molecules, these double bonds can move everywhere, right? Anywhere they can be found out, thought of founding out. And then doing so, they increase the stability because they give equal help to every bond, every sigma bond. And the bond length is then same. strength is same. And when we have a group where people have same strength, that group is stable. So that is what the stability gives by this, resonance and moving pi bond. Okay, let's move ahead. So we were talking about this carbon, this oxygen, and now how many sigma bonds are there? One, two, three, right? So what three? It means it is sp2, one lesser than that, right? sp2 hybridization is happening with this guy, this carbonyl carbon. Okay, that's clear. Okay, and what will be the shape? Shape will be, if you want to see the 3D shape of that, that will be somewhat like this, right? Trigonal planar shape we call it. So they'll be looking like that. Yeah, kind of a 3D figure. Okay, so here it is carbon. So here it will be hydrogen. Here can be an alkyl group, and here will be oxygen. And remember, the angle between them will be of 120 degree. So that 3D structure we can understand. Now you will say here the question can come like, this carbon, and if you say oxygen is here, does not that make a difference because it has a double bond? Remember that shape of the molecule, shape of the molecule depends on depends on sigma bond, not the pi bond. Pi bonds are weak. So who defines actually the shape? The sigma bond. So that's why when I'm drawing this structure, I'm just worried about the sigma bond. So these are sigma bonds, strong bonds. Okay, so that's how we see the trigonal planar structure of aldehyde. Okay, so now I know that we are talking about this hybridization. So I think we should have a small review here about like what I mean by sp2 hybridization and this one. So let's have a small review of that, and then we will move ahead because I think this is important. Okay, so just a small revision on that. Okay, so if you understand like what is carbon, okay, it has atomic number of 6. Okay, it has atomic number of 6. If we want to write the configuration of it, we can say it will be 1s2, 2s2, 2p2. Okay, now think about it. What are these different things? We have to name them. So this 1, 2, which you are seeing in front, these numbers are the main shells. Main shells. What is this S, S, SP? What are these? These are the subshells. Subshells. And what are these numbers now? So these are number of electrons. These are number of electrons. So clear? If we are seeing the configuration, we should be able to read it. So what we are seeing here is the first energy shell, first shell having subshell S, and then we are having number of electrons in that too. What about this? It's the second main shell. We are talking about p subshell of that, and that p subshell has number of electron as 2. So if you see 2 plus 2 is 4, 4 plus 2 is 6. That's why we show the configuration of carbon 6. Okay, and now how to show in orbitals? Let's see. So for orbitals, we will draw diagrams like rectangles like that, like that. So this is, I want to show 1s orbital. Okay, so this is 1s orbital. So how to write them? 1s2 means one electron will be here like that. Okay, just showing how it is. So if we are doing upward direction, it means the electron is spinning clockwise. So remember that. If I'm doing like that, it means clockwise. Okay, spin. Or you can also, we call them upward spin, right? Upward spin. Okay, the second electron will be not in the same direction. It will be having opposite spin, right? Downward spin, or you will say anti-clockwise spin or counterclockwise spin, right? Or you can call it downward spin. Yeah. So this is what I have shown here, you the 1s2 orbital. Now what about this? Okay, let me write this also. So this is, I am trying to draw and represent 2s2. So here auto one clockwise spin and one anti-clockwise spin. So they have two. Now what about this? Okay, so the P has three axes. So it is not spherical as this. It can only have two, but P can have three orbitals like this. Okay. So it is like one is for, if you see it, the p orbital shape is like that. So it can be on the like y-axis, it can be like x-axis, and it can be also like 3D. I'm showing z-axis. So three orbitals representing these three, and each can have two electrons. So now how much is remaining? 2p2. So we will do this, okay, and we will do this. So now this is 1s2, 2s2, and this is 2p2. But now think about it, why I have not placed it here, right? I should have put the second electron here. Why I have not done that? Because there is a rule. Okay, so we'll follow this guy. We'll follow this rule, Hunt rules, Hunt's rules. So whenever we are filling same energy orbitals, same energy orbitals, okay, we have a fancy name that for that, degenerated, degenerate orbitals. Whenever we are filling them, first what you need to do, first singly fill them, okay, singly fill with parallel spin, like what we have done here. Parallel spin means it is going up, this also going up. Don't pair them, you know, when you are putting them in these orbitals. So first singly place them one by one. Okay, what after that? After that you start pairing. Okay, after that we pair. Okay, and how we pair it? We don't go with the same same direction. We go anti-parallel. So if I want, I had one more, I will place one more here, and then I will start pairing with this one, with going, in the opposite direction. We will understand this when we are going next. So now what we are seeing here is the ground state of carbon. So this is the ground state. Okay. And now the fun begins. What if the carbons is excited? What will be the hybridization in that case? So I'm talking about the excited state now. So it will be the change. The arrangement can change how the electrons are filled in the orbital. Okay. And now you will see, if you focus here, the ground state is not showing the tetravalency, right? Only these are single ones which can be paired. So in the excited state, you will be able to see the tetravalency of carbon. So let's understand that. So I'm showing six carbon 6 as this. And now what happens? This is 1s2. Okay. This was 2s2. And this was our p orbitals, 3 p orbitals. And we had like this. Okay. And according to Hund's rule, we only kept one and this. In the excited state, okay, because these are in the same energy level. Okay, these are all in second main shell. Remember that 2s2 this is, and 2p2 this is, right? So these are in the same energy level. So in the excited state, the electron which is got paired here can go here. So it'll be like this. Ah, that looks good, right? And that is what the four, carbon bonds which it can make. And this, if we have this kind of a state, okay, this is what we call atomic orbital. Atomic orbital. And that is what here you are seeing, the tetravalency of carbon. Yeah. But we still have a problem. See, this was of S shape, right? A spherical shape. And these three have lobes. So what will happen? They will say, okay, we have to hybrid ourselves. Like, for example, think about hybrid, like you have hybrid cars. So that has a, diesel also you can put in that, and you can use the battery also. It is hybrid mix in a way. And mixing them, we are getting a different performance, different feature of the car, right? Similarly, here it is S and P, and combining them, they will give us a different thing. They will overlap with each other and will give us a totally different shape. They will hybrid ourselves. And how much? They will give us four hybrid orbitals. So this is the rule. Remember that if we are mixing, okay, if we are four atomic orbitals, so here are four atomic orbitals. So if they overlap, so they will give again us the numbers will remain same, the four hybrid orbitals. Okay. So now what kind of hybrid orbitals we will get a result of that if all these four of the second shell, overlap with each other? The four hybrid orbitals, what we can call them? Think about it. S and P 1, 2, 3. So that is what we will get. One sp3. These are hybrid orbitals. Second sp3, third sp3, and fourth sp3. Four hybrid orbitals in front of you, and they will make bonds. Remember that. Okay, so this is what the carbon hybridization looked like. Okay, now here in this case, they will only make sigma bonds. They will have one lone pair, right? One electron here, and that can be create bonds with others. But where is my pi bond, right? That is what we are interested in. I'm interested in pi bond who can be delocalized, right? So that you will see in a different probability, which we are going next. Think about it. So in the excited state, okay, this is 1s2, okay, and this is 2s2, and we saw in the excited state, one electron which was paired here can. So this can happen, right? So we, and the last one which we did sp3 hybridization, okay, sp3. But that can be the case also when only this overlap, or sp2 only will overlap, right? So the overlap is happening only this. And what is this guy? Oh, he is free to move, right? And that is what is called, this will be unhybridized, right? It is not taking part in this overlap, dized, unhybridized orbital. So this is what it is. It is not overlapped. And this is what our fancy bond, the pi bond, right? This is what we were talking about. The lateral overlap will do with the oxygen, right? And what these will give, okay, this will give three hybrid orbitals. Name of them will be sp2, right? One more, sp2. If there are three atomic orbitals, they will give us three hybrid orbitals, sp2. So that's why the three sigma bonds are giving a structure like this, okay, like this, okay, trigonal planar, and this is 120-degree, right? This is the shape, 3D trigonal planar, trigonal planar. So now let's look at the electronegativity of carbon and oxygen. Okay, so what the difference that makes, that we need to understand, and that is very important when we are seeing how it will bond, how it will react. So we are going to that direction now. So let me draw aldehyde now. This is a double bond. Here's the alkyl group. Here's our hydrogen. Yeah. So we now identify it very easily, like what is aldehyde looks like. So it looks like this. Now you know that oxygen atom is more electronegative. More electronegative. It shares a bond, but it pulls the electrons more on its side. Not completely, but little bit partially. So that will get a partial negative charge on this. And that, due to the partial deficiency here, it will get partial positive charge on the carbon. Okay. Now think about it. What will happen in this? Okay. So we will call this thing, it has become electron deficient, right? So this carbon will be called carbonyl carbon is electron deficient, right? Or we can say what it needs, electron, right? It will like electron. So the nature is electrophilic. Electrophilic. Its nature. Okay. Carbonyl carbon has electrophilic nature, or we can say it is a electrophile, electronphile. Okay, this is what we call a Lewis acid. This is the definition of that. Okay, what do you mean by that Lewis acid? It can accept pair of electrons. Okay, so remember that. What about oxygen? The carbonyl oxygen. So I'm talking about this now. Okay, so this is electrophilic in nature, right? Electron deficient center, we call that. Okay, so we call that electrodeficient center. So carbonyl oxygen, if you see, there is a negative charge on that, right? And this also will have two lone pairs also, two lone pairs, which we don't show generally, but they are there. They are not taking part in bonding. Okay, we call them non-bonding electron pair, non-bonding electron pairs. So that is what the situation for this oxygen is. It's more electronegative. It has extra pairs which are not taking care of the bonding. So what can happen due to this? So due to this, the oxygen we can call is electron rich center. Yeah, electron rich center. Or we can say it is a nucleophile. Nucleophile. Okay. And this is what we call the Lewis base. Because why? It can donate pair of electrons. So now we also detailed the charges, how the charges situation is with the carbonyl carbon and carbonyl and oxygen. Carbonyl oxygen. Okay. So if you see what will happen, going to happen in the reaction and what we are going to see in the future, that we need to discuss now. So now when we start reacting, how it will react will depend on this. So here is our aldehyde group, right? So what is going to happen is, this pi bond can break, and this can become electron rich and this can become electron deficient, right? So this is will can be like that, positive charge can come here and like that. So it can become, you can say, dipolar, right? Two poles, it can become dipolar. And now let's see, due to this, what this carbon can take, right? This carbon can take a nucleophile. So it will show nucleophilic addition. If any other thing wants a nucleus or a positive, it will come to this carbon, the carbonyl carbon, and get attached with this. So the carbonyl carbon will show nucleophilic addition. Let's take an example. Like for example, I have like that carbon. I'm just putting it this way now. Okay. And I have a molecule like this, which is NaCN. Like NaCl, I'm showing NaCN. So this has negative and this is positive. So the if you see the nucleophile part is this. Nucleophile means it wants nucleus or positive charge. So this will be nucleophile, right? And this will be electrophile, right? It wants electron, it wants to have nucleus. So now if we react them, what can happen is we know we can show it like that. Oxygen can go like that, and Cn can come over and attach here because due to this positive, right? Pi bond broke, negative went here, carbon got its, you know, negative charge from this nucleophile. So this nucleophile can attach here, Cn can get attached here. So if you see what it got added, the nucleophile got added to the carbonyl carbon. That's why we are saying it will show nucleophilic addition. Okay, and what will happen after this? See, these can't survive, only negative charge, this can't survive. So the Na, which is the positive one, which get attached here, O and A. So this is how we can see, that how nucleophilic addition is happening, because our carbonyl carbon is, a positive. So whoever wants positive or whoever wants nucleus can come and add here, right? The electron will come and added here, and it will create a bond here. And that's how the addition is happening. So the nucleophilic addition will take place in case of aldehydes. Remember that the same thing will happen with the ketones. That's why we are reading ketones also. But we have a difference. Let's see the difference. Okay. So the summary of this little short part was that aldehydes will show nucleophilic addition. The carbon will attract nucleophiles, and that's why the bonding is happening and will happen. And that's what we will see when we are doing preparation and reactions of aldehydes and ketones. So let me write a structure of here aldehyde. So one at least hydrogen should be there, right? And ketones, similar to that, look similar, but they are like that. No H, right? No H. So both are having alkyl group, both sides. This carbonyl carbon is having both sides, both arms are alkyl groups. So this is what we called ketone. That's why the chapter name is aldehydes and ketones, right? They have similar properties, we can say. They show nucleophilic addition, right? Nucleophilic addition or a nucleophilic molecule, atom, ion can be added here. And this also will show nucleophilic addition. Both will show the nucleophilic addition. In this case also, there is somewhat positive or electron deficiency here. So the nucleophile can come and grab this positive or a nucleus. But here also, this is electron deficient. So a nucleophile can come here and get this nucleus or positive. So that is how the nucleophilic addition is common for both of them. But what is the difference then? This is not fast. This is the slow nucleophilic addition. It shows slow nucleophilic addition. But in this case, it is fast. You can say it is convenient. Why is that? The answer is very simple. See, it is a bigger molecule. The size is big. Okay. And when a nucleophile is coming, it is having more resistance, you can say. And we have a fancy word for that, steric repulsion. Okay. Steric repulsion due to bigger size of that. Okay, they are already stable, they are a big group, so a new person coming in will be difficult. But in this case, it will happen fast. Nucleophilic addition will happen fast because there is H1 here. So they are not as big. So the steric repulsion will be less and the nucleophile will be attached in this carbon. Okay, so remember that. And being said that, because of this addition is happening in the case of aldehyde fast, we can say aldehydes are more reactive than ketone. That is what our summary here.